Hi guys, today I'll just give you a small lecture regarding Kirchhoff's current law, and I hope just you know the meaning of what's Kirchhoff's current law. It is actually that the summation of currents at any junction, it is zero. Supposing this is one particular junction or a node, here you have the incoming and outgoing currents. So if you algebraically sum all those currents, both incoming and outgoing, the summation is equal to 0. The algebraic sum actually is equal to 0. And for a small illustration of the KCL, you can watch my video, subscribe to my channel, and watch the previous video of this electrical lecture online for a small illustration of KCL along with the KVL for a smaller circuit. And this is now actually an extended DC circuit with 3 meshes. That's why I'm saying here it is a 3 mesh DC circuit. Actually I'm dealing with a bigger circuit compared to the earlier small circuit which I did in the previous video. And during this explanation of this entire clip of this video, if you feel if you don't understand anything, you can just scroll back and drag your along the timeline to view the explanation for one more time, just to remind you that I'm saying you do not feel that you're missing something. So that now we're going to apply node analysis for this simple 3 mesh circuit. The mesh is actually nothing but the one closed loop. So here you can identify 3 such closed loops, so you can call them a mesh DC circuit. And now this would be a lot easier when you apply Kirchhoff's voltage law. But now in order to apply the Kirchhoff's current law and study how does it behaves through the circuit, we will study a node analysis solution method which applies the Kirchhoff's current law. And let's just solve for the voltage appearing at each and every nodes and the current flow across these 2 branches. So I'll just give a small demonstration about how to analyze what are the nodes in the circuit. Since it is a node analysis, we just have to first identify what are the nodes in the circuit. So the next slide will show you what are the nodes in the previous circuit. If you see, it was just a circuit. Now I have marked the nodes here, 1 2 3 4 5. There are 6 nodes with V1 V2 V3 V4 named in clockwise direction, and then V5, and the reference voltage is ground, which is 0 volts. So there are 6 nodes, V5 and 6 nodes. And these 2 points are not called as nodes because this part is just a wire. You see, in the previous circuit, if you were supposed to identify the nodes are only 6. That's 1 2 3 4 5 6. These 2 points are not nodes because it is just a wire that is connected. But this is not just a wire, it has a voltage source, and this is one element. This is one element. This is a resistor element, and this is a voltage independent voltage source element. Both are connected through one node. So there is a voltage appearing at this point. Now if you would ask me, if you connect a multimeter at this particular point and measure the voltage, what would be the voltage that a multimeter would see here, even if it is a digital multimeter or anything, according to even your calculations? You don't have to assume that it will be 12 volts, since here you have the 12 volts and this is the plus side and this is the minus side. Doesn't mean that plus 12 volts will appear here. At this point, the voltage that will appear, it will be slightly lesser than 12 volts, and it may be slightly higher than 12 volts. It actually is slightly higher than 12 volts. So we'll find out why it happens, why this particular 12 volts doesn't appear at this particular node. So all the voltage levels at different nodes are different, so we have to find out that. So we have first identified the number of nodes. There are 6 nodes, as in the circuit we see 6 nodes are there. Each node has its own voltage point identified as V1, V2, V3, V4, V5 and the reference point. And as I said a while back, this 12 volt, since it is plus, you should not assume that this plus 12 volts will appear here. A different voltage called V4 will appear between these 2 elements, that is the resistor element and the voltage source element. different voltage V4 will appear, and we will find all the voltage sources and the currents across the elements. So we'll apply the node voltage analysis. Since we have identified all the nodes, now we'll go for the node voltage analysis. Now see the reference diagram, I have just kept that the same. I have just used this previous slide. If you see, this was the identified nodes diagram. I have just taken that into this slide, included that as a reference diagram, and I have marked two currents and I have assumed the directions. If in case I happen to solve and get a negative value for a current, that means I have just assumed the wrong direction, so it is going to flow in the opposite direction if it is going to show a negative value. As of now, I'm sorry, as of now we just assume that these two currents flow in these two directions, and we will solve for the voltage levels. So for that, in first you have to develop the nodal equations. Now what is a nodal equation? For example, you are applying the nodal Kirchhoff law, current law at this node V1, this point. It means that you are finding the sum of currents at this particular point. So this is V1 minus V4 divided by 2. It means this is V1, this voltage, when looking from this point you should say V1 minus V4. You are considering this as the higher voltage. Since the current flows from a higher voltage to a lower voltage, you are considering the V1. When you apply the Kirchhoff current law at one particular node, you by default have to assume that that voltage is a higher voltage. So it is V1 minus V4, not V4 minus V1. The sign matters a lot. So it is V1 minus V4, the voltage difference by the resistance 2 ohms, which is equal to the current according to the Ohm's law. Now this is one current which flows from here to here, so it is an outward flowing current. According to my calculations, I have assumed all the outgoing currents as positive, so it is plus, and plus need not be shown, it is plus as plus. So it is plus V1 minus V4 divided by 2. All the outgoing currents are assumed as plus and all the incoming currents are assumed as minus. So this first equation of the first current is V1 minus V4 divided by 2, V1 minus V4 divided by 2, and the other current is this current, which is going to flow from V1 to the reference. So it is V1 minus 0 divided by 2 again. It appears here, and this is V1 minus V2 divided by 3. Let's see that. This is this current, V1 minus V2 divided by 3. Now from this point there are three, at this node there are three branches, so there are three currents, so there is nothing to be confused about. In the same way you have to apply it for all other nodes. Now I will not just skip the lecture, I will just illustrate each and every node for the practice of the listener. Coming to this point, node 2, you have V2. Now V2, from V2 there are three currents flowing outwards. It may flow outwards or inwards. As of now we'll assume that it is flowing outwards, since we have not assumed at this point. When you see IY, it is flowing inwards, so we'll be having a minus sign assigned there. But as of now we are having this node as identified as V2. We will solve the currents at that point. We have three currents. The first current is V2 minus V1 divided by 3, which you see here, V2 minus V1 divided by 3 is one current. And second current is V2 minus V2 minus 0 divided by 4, V2 minus 0 divided by 4, and this is V2 minus V3 divided by 5. So this is V2 minus V3 divided by 5. Now these, all the three currents summed up equal to 0. Now it comes to the other node, which is V3. At this point V3 is assumed as a higher voltage, so by default it is the higher voltage, and there are three branches, so there are three currents. Now one of the current we have already assumed as Ix, so it is incoming, so it is minus Ix, and the Iy is outgoing, so it is plus Iy, minus Ix plus Iy plus this current, which is nothing but V3 minus V2, because V3 is considered as the higher voltage because we're talking about the node which has the voltage V3. So V3 minus V2 divided by 5. Now this summation is equal to 0. When I come to V4 node, at the point where the voltage identifies V4, we have two currents. One is incoming, it is minus IY, and one is outgoing, which is V4, the higher voltage V4 minus V1 divided by 2. And this is the summation is equal to 0. And let's come to the fifth and the final node, where you have one outgoing current as Ix, it is plus Ix, and the other current is flowing through this 1 ohms resistor element, and there you have V5 minus this ground voltage, which is 0 volts. So you have V5 minus 0 divided by 1. So these are all the 5 equations that I have developed just like that. By nodal analysis, but these equations don't seem like you can solve them, so you have to take the LCM, multiply, and arrive at a set of simultaneous equations. So when you arrive at a set of simultaneous equations, you have to keep one thing in mind, how many equations you have and how many unknown variables you have. At this point of time, when you see at this page, you have 5 sets of equations with almost 7 unknown variables, and the 7 unknown variables are V1, V2, V3, V4, V5, 5 voltages and 2 currents, Ix and Iy. So these are all unknown. You need 2 more equations, and those 2 equations we can get from the circuit information, where you see that we'll just go to the next slide for that. There you can see this voltage difference, which is V4, the positive side of the 12 volts, which is V4 minus V3 is equal to 12. This is what it implies. This is an independent voltage source of a value 12. This voltage of 12 volts is identified by the difference of 2 potentials, which is V4 and V3, and now we consider the V4 to be the higher side because of the positive side of the 12 volts. This is the bigger line which shows it is positive and this is negative, so the positive side is a higher voltage, so that's why I consider it as V4 minus V3. It is V4 minus V3, not the other way around. Please don't mistake with the signs, otherwise we will arrive at a big mistake and we will not get any correct values of any voltage or current. The most important thing throughout the analysis is the signs of the values. If you assign the wrong signs, you are completely out of the calculation. So the next identification of the 18 volts is the difference between these two potentials. For this 18 volts, the higher voltage side on the positive side is the V3. So I have considered as the V3 minus V5 is equal to 18. So these are 2 additional set of equations along with these existing 5 equations that I had shown previously. And along with that, the 5 equations, we have existing equations 5 plus 2, 7 equations and 7 unknown variables, V1 to V5 and Ix and Iy. So there are 7 variables and 7 equations. Now you need to solve these equations. For solving, you first need to arrange them. Now this, when rearranged, for example, I will say this, the LCM, when you take this number to be multiplied with this numerator is 3 into 2, 6. So it is 6v1 minus 6v4 plus 2 into 2, 4. 4v1 minus 4v2 plus 2 into 3, 6. 6v1 is equal to 0. The equation will turn out to somewhat like this. The equivalent equation, I have just taken down all these equations and written in the left side, and the rearranged equations I have written on the right side, so that you can have the rearranged equations view easily. The first remains the same, second also remains the same, and the third equation I have kept at the bottom of the page. It is rewritten as here. It is simply V5 plus Ix is equal to 0. The fourth equation is V4 minus V1 divided by 2 minus Iy, which when solved gives this form. That's pretty easy. When you get at equation number 5, that's pretty easy too. You just have to take this LCM, 5 multiplied with these 2 numbers, and take on the other side and then rearrange. It is V3 minus V2 minus 5Ix minus 5Iy. So the last 2 equations are taking a bit a while. The sixth equation is nothing but the LCM is 12, 4 into 3, 12, 12v2 minus 12v3 plus this 5 into 3, 15v2 plus V2 minus V1 multiplied by 5 into 420. So you have this 20, 12 and 47, the summation of all the voltages, coefficients rearranged. It gives this form. The same way you develop the seventh equation. You just have to write it down and then solve it. And this is called rearranging. And by rearranging, we get one thing straight, that there are 7 equations with 7 different variables, and all the 7 variables can be assigned an equivalent coefficient. Right now, if you talk about the first equation, here all the 7 unknowns can be written in such a manner that the V1 has a 0 coefficient. So 0 multiplied by V1 is 0 again, plus again 0 V2 plus 0 V3. No, 0 V3 won't come because we have a V3 here, and then V4 plus 0 V5 plus 0 Ix. And similarly, we can assign the coefficients of each and every equation. And now by assigning the coefficients and identifying the coefficients of each and every value, each and every variable, it's pretty easy to solve that and eliminate them. But still then you have to sit with a pen and paper and keep on solving the equations, which is very hectic. Instead of that, you can just go online after identifying all these, arranging all these equations in a particular fashion and identifying all the coefficients or the variables of the simultaneous equations. You can go online and solve it. Before that, you just have this table. I'll just explain that it's very simple. As I said a while back, I was discussing about the coefficients. These are the coefficients of V1. When you talk about equation number 1, our equation was like this. And you see the V1, V2, V5 are absent. So you will find here V1 0, V2 0 and V5, V4 as 0. Now V3 and V5 are existing. So V3 minus V5. So this is what it is. V3 minus V5 is equal to 18, is equal to 18. At this point I had just made a small mistake, that it is equation number 2 actually, and equation number 1 is written in the bottom, which has a constant as 12. Now you see the constant is 12, for which only V4 and V3 exist. So this is equation number 2 actually. When you see the equation number 2 written down, the coefficient, the constant is 12, and we had only V3 and V4, so it is V4 minus V3 is equal to 12. So it is V4 minus V3 is equal to 12. This first equation is actually in the table, it is written down as second equation. The other things remain the same. For example, I'll take the sixth equation. In the sixth equation, you see 47, 12 and 20 assigned for V1, V3 and V2. Now you see V1 has a coefficient of minus 20. The sixth equation, V1 minus 20, V2 47, and V2 is 47 and V3 is minus 12. So V3 is minus 12. The rest are 0 and the equation number is 6 and the constant is 0. You see the constant is 0. In this way all the coefficients are taken out in a table. So what next? Is just next thing is very simple. It is just again entering all these values in a single platform which looks like this. And now what's this? This is actually a website. I'll just open the website and show it to you. There we have equation 1, 2, 3, 4, 5, 6, 7 equations, and Q, R, S, T, U, V, W. There are 7 variables, and this is Q, R, S, T, U, V, W is nothing but V1, V2, V3, V4, V5 and Ix and Iy. So we can solve for the coefficient. We have to enter the coefficients. Now if you see, the entered coefficient is 0, 0, 1, 0, minus 1. So it is 0, 0, 1, 0, minus 1 and 0, 0, 18. So it is 0, 0, 18, equation number 1 finished. And same way, fill all the 7 equations coefficient, and when you click solve, the rounding of 2 decimal places, all the 7 variables are solved here. So these are nothing but voltage. Q to U is nothing, Q, R, S, T, U. Q to U is nothing but the voltage levels. It is V1, V2, V3, V4 and V5, and it is Ix and Iy. Now I would show you exactly how does it happen in online. When you see, this is the website actually, idomaths.com, and when you see, there are different methods to solve them, and there is a drop down list. You have 7 variables and 7 unknowns. Here when you scroll down, you have 10 up to 10 variables and 10 unknowns. So there are lots of equations, up to 10 simultaneous equations you can solve. So even the circuit, if it gets complex, more complex, you have still the website to help you out. This is actually a simultaneous, very nice tool to just reduce your time here. As I said a while back, I have entered all the coefficients exactly as in the table. If supposing I just do one simple mistake, like I am doing here 1, so it is, instead of 0 it has become 10 now. If I now click solve, the entire set of values will change and the answer will be wrong actually. So this has changed and all the answers are wrong. So you just be careful while entering all the coefficients. It's actually 0, not 1. So now if you see q is equal to 2.41 will change when I click solve. It is actually a different value and it's just taking a while. Yeah, q is equal to 10.72 volts. This is actually 10.72 volts because q corresponds to the first variable, which is nothing but v1. Similarly for r, s, t and u for v2, v3, v4 and v5 respectively. So these two last variables are ix and iy. So according to that I have constructed this table q, r, s, t, u, v and w. So we got the values as in the website here. You can see I have just taken a snapshot of that, of those values: 10.72, 7.52, 11.57, 23.57 and minus 6.43. All these are volts. Now just look at the circuit when you rewrite all these values according to the voltage levels corresponding at the nodes. You find that V1 10.72, 7.52, 11.57, 23.57 minus 6.43. This is exactly what was there solved out, and the last two values are current, which is 6.43 and minus 5.62. and now you see the minus sign indicates that the direction was assumed in the wrong direction, because we said it was going to go this way, but now since the sign is minus, we are going to go let the current go this way actually, which is marked in the dotted lines. So it is going to flow towards V3. So both these currents flow towards V3, and the voltage levels identified here as V1 is 10.72, V2 is 7.52. So V1 is here 10.72 and V2 is 7.52. So all the values, when clearly indicated in the circuit, it looks somewhat like this now. So you have all the websites solved for the values. For instance, S is 11.57, it is V1, V2 and V3. So V3 is 11.57. When you come here, the V3 is 11.57 volts with a current of IY 5.62 amperes flowing towards V3. So this is just a mouse clicking procedure almost in the website. You just enter the coefficients, and for the coefficients you have to rearrange a set of simultaneous equations. You have to have the same number of equations as you have the number of unknown variables. For instance, in this case our three mesh DC circuit had to solve this 3-mesh DC circuit we had 7 unknown variables. So you have to have 7 simultaneous equations to solve them and arrive at these values. So when you want to check, if you want to really check these values if they are correct or not, you can actually have a color coded resistor identified for these values of ohms, and you can actually use a PCB, printed circuit board, and pin all the resistor values, and then use a multimeter with 2 voltage sources connected. You can use a multimeter to measure all the voltages and currents across different points. You will find exactly near about the same voltage and current levels here as shown. Maybe there may be some variations, because actually in practical cases, along with the calibration errors and the color coding of the resistor, there is a temperature coefficient of resistor which changes with the room temperature. So there might be some variations, like say for example plus or minus 0.5 or plus or minus maximum of 0.8% error in the readings. Otherwise you will get the same values if you test this circuit for your readings. Apart from that, this was actually a nodal analysis report of the circuit, and so this is how you solve using a node analysis. You just have to identify the nodes first and assign the voltages and develop the equations for each and every node, rearrange them in form of simultaneous equations, and then feed in the website, get the values, and then superimpose those values again on the circuit. It's as simple as that. Until next time, goodbye.